Okay, so quick announcement. That is about 95% of the way to working, Ariel. It's this close. But it is almost the end of the semester, and we have to wrap up some things. Okay, so I need to hear from you very soon if you're planning on taking the midterm replacement. Beer tasting class is not too far off from coming at some point too. Okay, so if you want to do the essay, you need to talk to me and let me know very, very soon, like today or tomorrow, kind of soon. Okay. And we do have a very, very, very awkward public service announcement. So I would just want to point out to everybody, for your future benefit, that when you post things to Chegg or look at things from Chegg, your instructor can get that information. Okay, guys? Now, of course, the questions that were posted from the midterm were not answered. So no one got any help from it. But man, you were like this close to putting me in a really, really bad spot with having to report people for honor code violations on this, right? So don't do it. And also, every professor can learn when you post things, right? Or when you look at things, right? So don't be stupid, okay? Public service announcement. And let's get on with the science. So where did we leave off on sintering? Okay. Okay, so we were talking about the initial, intermediate, and final stages of sintering, right? And when at first the initial, we have a powder compact where the material is rigid, and just in contact at one point, right? And then as we start to sinter, the neck region grows, and we get large planar contact area between the grains with large pores in between. As we go on, right? As we go on, our pores become these elongated channels that are at the edges of these faces. And this is an intermediate stage sintering regime. And then the pores on the edges begin to close up, and we're left with pores on these vertices. Okay. And now this is a I don't know how to interpret that. Um, oh, I hope your computer's okay. I hope you're okay. Um, so you're left with just isolated pores at the corners, at the vertices of these polyhedra. Now, of course, this is highly idealized, and these polyhedras, when we talk about grain growth later today, we'll realize that these are actually curved surfaces, not perfectly flat. Okay, and so how do we actually um, close up these pores, right? Okay. Well, so one model of these is this. It's actually a well-known model. It's probably the um, only time where we have a large polyhedra, the geometric name. So it's the tetrachedron model of intermediate stage sintering. And so what we have is a polyhedra that's made up by the intersection of all of these particles, and we have a elongated cylindrical pore channel. Okay, so we have vacancies that are diffusing along the grain boundary or through the bulk, but from the surface of this pore, right? And we know from diffusion, if vacancies are nucleating at this pore and diffusing into our grain boundary area, that means that mass, we have to have material diffusing this way, right? If we have a net flux of vacancies away from the pore, we have to have a net flux of atoms towards the pore, right? And that our grain boundary here serves as our sink where our vacancies are annihilated, right? And that's how we eliminate the pores, right? And this is just essentially another picture showing the same thing. Okay, so what about the effect of the geometry of our pores? Okay, so our pore shape and our pore volume fraction is continually evolving during our sintering process, right? And this model here assumes that the pore is going to be continuously shrinking during sintering. But there are conditions where pores can become thermodynamically stable. Okay. So here we have 4 grains intersecting, right? And we have, in this case, a square pore channel, right? Just for simplicity. And we allow this pore to shrink, right? We go from this line here. So during this increment, during some time increment, the pore has shrunk by this amount. Okay. So what is the the energy eliminated, right? So we can do our geometry and figure out how much of this solid vapor interface we're eliminating versus how much grain boundary area we're eliminating, right? And we end up with a ratio that looks like this, right? And so essentially, if we have a balance between the grain boundary energy and the solid vapor surface energy that is of this form, right, where our grain boundary is less than 2 times our solid vapor surface area times the angle, the contact angle here, then this pore is going to shrink. Okay, so if we then assume sort of standard values for this grain boundary energy and this solid vapor surface energy, what we see is we can come up with a coordination number for the pore, where the pore will shrink, and a coordination, so as long as it's less than this value here, the pore is going to be eliminated. If it's larger, the pore is going to be stable, right? So, okay, so that's just an expression. How does it look in practice? Essentially, here on the right, we have a pore that has a coordination of 3, right? So if we maintain our 120 degrees here, what shape does this need to be to maintain 120 degrees? This pore here is going to shrink, right? And over here, we have 6 grains surrounding. And now this pore here is going to be stable and grow. This is actually just stable. But we see here something interesting. We've got curvature to this pore interface, right? And this pore is going to shrink. Okay? So that means the easy way to remember it is when we have these concave surfaces that look like a cup, right? It's always going to grow. The grain is the interface is always going to grow in the concave up direction, right? So it's like a snowplow, right? Is another way to think of it. Right? So this pore is going to shrink. This is going to expand, right? This is just at the stable configuration. Okay. So we'll revisit this same idea again in grain growth, right? But essentially this shows that in order for a grain to grow, right? We can imagine if this is a grain surrounded by other grains, if this grain were to grow, it needs to have 6 sides. Anything smaller than that is going to shrink. And the same goes for pores. Okay, so very fast, liquid phase sintering. So liquid phase sintering describes sintering when a proportion of the material being sintered is in the liquid state. Okay. Liquid phase sintering is really of important commercial importance, since the majority of any ceramic product that we make, white goods, which is a generic term for ceramic bathroom fixtures like sinks and toilets, but also engineering ceramics like ferrite magnets, whole families of covalently bonded ceramics, ferroelectric capacitors, abrasives, among others. So, and then even a lot of products that are believed to be solid state sintering, it's been shown that there's actually a very, very thin film of liquid present at the grain boundaries. Very much like when we talked about solidification, how we said that many systems have a very thin layer of liquid on the solid at all times because it minimizes that interfacial energy. The solid liquid liquid vapor interface system was more energetically favorable than just the solid vapor interface. So a lot of what happens is in the liquid phase, most of the theory is completely developed for the solid state sintering, right? Liquid phase follows a lot of the same trends, except it's much more rapid. It has a much more uniform densification, and the presence of the liquid phase actually reduces friction between the particles, and that means and because you've got these sharp particles surrounded by liquid, now I have my Gibbs-Thompson melting enhancement. So any little sharp particles can melt back, and we get nice rounded edges, and all of that helps sintering. So the necessary condition is that the liquid needs to wet the solid, right? That's the key thing, right? It has to wet, so I need a dihedral angle here of less than 90 degrees. If it's 90 or greater, the liquid is just going to beat up into the pores and is not going to contribute at all to the sintering behavior. You basically just have solid state sintering with extra steps, right? Okay. So to see how liquid state sintering can help, right? Why wetting is crucial. We can imagine a capillary film between two solids. And if this dihedral angle is less than 90, the surface tension of this film is going to exert a compressive force and pull, well, depending here, it's going to be a tensile force on the liquid, but it's going to pull these plates together, right? So on these grains, there's actually a net compressive, right? Whereas if we have a dihedral angle of greater, we're going to push it away. The actual maximum overall is when it's exactly 90, but that's because there's other things going on. But that is in the reading, but we're not going to talk about here. The key thing is that if you have a dihedral angle of greater than 90 degrees, your liquid film is actually going to try and push your surfaces away, right? Which is the opposite of what you want. If it's 90 or less, you're going to have a net force pulling them together. Okay. And so we can compare here. This is, oh, I forget what the material system is. But anyway, you can see the effect of this is sintered at the same amount of time. You can see actually we have multiple phase particles. So we have powders that were made of multiple phases mixed together, put together in a mixture, and then sintered. And you can see the difference between that a thin grain boundary film of liquid makes. These were sintered under the same conditions, same time at temperature. This one on the right here is just slightly doped. So you had a little bit of eutectic melting in this one on the right, where we don't have that on the left, right? So you can see you not only have greater densification, but you also have much larger growth. Okay, so so during selected laser sintering, so SLS, yeah, you can't. You've got a little bit that you can do by controlling the laser power and the speed, right? But most of the time, those controls are completely essentially it's a black box control, right? You have like a knob or a setting that says power. But in reality, that's not just controlling the laser power, that's controlling the power, the dwell, and the speed, right? So it's controlling a whole bunch of stuff. So right now, additive for both metals and ceramics is much more of a hope it works kind of thing, right? There's you have very limited control of the actual machine, right? So it works a lot of the time, but sometimes it doesn't. So that means you're left with playing tricks like, well, what if I print it from the side instead of from the top bottom, right? What if I just rotate it 90 degrees on my build plate and I do it some other way? Maybe I can do it. It is getting a lot better, but it's still not anywhere near until you have additive manufacturing equipment manufacturers that are willing to completely open up their systems and open source their control software so that people can really control what's going on in their machine without voiding their warranty on a multi-million-dollar piece of equipment, then we're not going to be there, right? And in fact, it's it was sort of to the point that GE Aviation, when they were really looking at additive for parts, now they're flying additive parts, but several years ago, before, I should say, they're not flying any rotating parts, they're flying static parts like fuel nozzles that are additively manufactured. But when they were looking and trying to get the control they needed over the printers, the only way they could do it was to actually buy out a major equipment manufacturer so that they and own the company, and that was how they got access to the control of the machinery that they needed, right? So EOS is, I think, one of the prime holdups in this, right? They completely refuse to allow anything open. The German company Drumpf, not to be confused with our president, but Drumpf is made it a point of being of making their things much more open, and they're getting market share. Yeah, I know. I was part of the proposal that brought it there. So, okay. Well, anyway, grain growth. Okay. So, oh, I forgot to put the titles in. So grain growth is a really interesting phenomena, because what we actually see is that our microstructure is completely unstable. Right? Our grain structures that we see in polycrystals, metals or ceramics, we're not at any kind of metastable equilibrium with them, right? We're not anywhere close. We have a completely thermodynamically unstable system. right? That exists in the form that it is only because at room temperature, we do not have enough energy for diffusion, right? We can greatly reduce the energy of our system by coarsening our grains and removing all this interfacial energy, right? But we just don't have the kinetics to be able to do it, right? So any polycrystal is in the perfect analogy of a thermodynamically unstable system that we take advantage of and use every day, right? Okay. So I checked this morning. I screwed up the scheduling. So they are up now. But they were supposed to go live yesterday and for some reason didn't. But they are available now. Okay. So before we talked about the curvature in pores and how that leads to motion, right? Right? But what is the origin of that driving force for growth? And it's our good old friend Gibbs-Thompson, right? So remember, if we have a curved interface like this, the chemical potential here is under a concave surface is greater than under a convex, and there's a higher vacancy concentration here. So the atoms are going to jump from right to left. So that means the interface is going to move from left to right. Okay. And we see the same argument that we saw before for pores, is that when a grain has more than 6 sides, it's going to grow, and when it has less, it's going to shrink. Right? Okay. So, oh, I forgot. I talked about the partial pressures and curvatures in the sintering from Friday, right? So the complicating issue here, though, is that it's easy to picture in 2D, but the curvature in 3D is a little bit more complicated, right? So anytime we have curvature in one dimension, like a cylinder, right? This surface, right, our cylinder is only curved in one direction. We know that this cylindrical grain is going to shrink if it's surrounded by its neighbors here, right? If I have a planar interface, that's flat, no curvature, no driving force for motion. So a planar interface is going to be stable, right? But we also have another configuration where we can have no net force, and that's if we have a saddle, right? So if we have a compound curve and we're curved in 2 dimensions here, we're going to have no net force. Okay. So if planar interfaces and perfect balanced saddle structures are the only curves in 3D that give us no net force, that means a polycrystalline aggregate is always, all of the grain boundaries are going to want to move as soon as you heat it up, right? And all of the unbalanced forces are going to cause all of the grains to move, migrate towards their centers of curvature. Okay. So depending on the configuration, 6 sides, right? It all depends on the actual curvature of the grain boundary, right? So this this 6-side argument here, this is for 2D, right? And it's a rule of thumb, right? So things can happen because the grain boundary energy isn't isotropic. The interfacial energy isn't isotropic. So it's going to depend on the exact orientation relationship between two grains as to what this curvature is going to look like and which way it's going to go. Right? So the 6 or more is just a rule of thumb. Right? Because the actual situation is more complex. Okay? So here's just sort of another picture, right? And if you maintain a dihedral angle of 120 degrees, if we assume that these grain boundaries are isotropic, 3 shrinks, 4 shrinks, 6 gives you a perfect hexagon, so planar interface, it doesn't move, and more than 6 is going to grow. Right? But again, this is highly idealized, and you never actually see these star-shaped grains. Right? So there was a really famous experiment from Cyril Stanley Smith in 1952, where they worked out a lot of the coarsening kinetics by looking at microfluid, or soap films. Right? Now we can't call them soap films; we have to call them microfluids. But we have we can record how they actually behave, right? And you can see all the grains with grain boundaries that are concave are going to be shrinking, right? So we can predict which grains are going to grow and which grains are going to shrink, right? Which way interfaces are moving, right? And if you look carefully, sometimes you can see interfaces on some grains where one part of it shrinking and one part of it is growing, so that can actually happen. I like these little arrangements, right? But you can see that when a grain is eliminated, the neighboring grains all rearrange themselves as the surface tension pulls it in different directions, and that coarsening happens very quickly when the grains are small and there's a large number of them. But as it goes on, the grains become larger, the curvature of each boundary becomes less and less, and the overall coarsening and grain growth kinetics slows down. Right? Right? So we can zoom ahead, right? And when the time we're out here, we still see these interfaces moving, right? But they're moving very, very slowly relative to what there is before, right? And a lot of the curvature that we see here is actually due to the interface effect, that this is a finite volume and we have a different surface energy with respect to the wall here. Right? So you can see those you can see those effects, right? But even though it's a 2D picture and it's a soap bubble, our real grains behave very much in the same way, right? Our 3D grains coarsen in exactly the same way, and they rearrange due to the interfacial tension in exactly the same way. It just happens very, very, very slowly at lower temperatures. And it's not until we get enough diffusion, enough thermal energy to overcome the diffusion barrier, that it can happen in a finite amount of time. So coarseness, so we refer to coarsening as the evolution from a large amount of very small grains to a small amount of very large grains. And those generally are referred to as fine grains and coarse grains, right? For historical reasons. Small grains or large grains, right? So this process of grain growth is coarsening of the microstructure. Okay, so we can do a little bit of analysis and calculate what the force on that grain boundary is, right? So if we just think of our standard model that we've used this whole time, right? And we have a atom that's jumping from grain 1 to grain 2. In grain 2, it's in a slightly more stable configuration. So there's a net change in free energy of delta G, but we have a activation hump barrier that we need to overcome for this jump to happen. Okay, so you can see where this is going now, right? This is going to look like our Boltzmann statistics, right? The atomic picture is we have grain 1 is shrinking, grain 2 is growing. We have these ledges of close packed atoms, right? And we're going to have a net number of jumps from one close packed plane in grain 1 to a close packed plane in grain 2, right? That's sort of our simple atomic model, right? Of course, the free volume in this is larger, it's exaggerated, right? The grain boundaries, the atoms actually fit more closely together than in this picture, right? But it's a good schematic to look at, right? And so we can use our Gibbs-Thompson expression and relate our change in Gibbs free energy to the surface energy, right? Or our change in chemical potential, right? Remember, chemical potential is just the partial molar Gibbs free energy, right? And so essentially our change in our driving force for grain growth from our Gibbs-Thompson is 2 times our surface energy. This is the molar volume of our solid, and R here is the radius of curvature of our grains, right? And so we can set up a little schematic and we can say, if I have this interface and it's moving from this point to this point with some force acting on it, right? We know what the force is. The force pulling is just going to be our change in Gibbs free energy, right? So we know how to express that. We can do a balance, and then we can do a little bit of diffusional work and consider the probabilities of jumping from one side to the other under the driving force, and we can calculate a flux, right? And this flux term should not be at all surprising to you from the diffusion work, right? What does it have in it? It has our activation area. Oh, sorry. It has our activation barrier, and it has our net free energy gain, right? So this is derived more carefully in the reading, and then it's got the prefactor. Okay, it's got the vibrational frequency, the number of atoms, and a geometric factor, right? But anyway, this should be at this point kind of an intuitive relationship to you, right? This exponential, what this exponential form looks like. And so that means we can calculate the velocity from this, right? And we end up with a Gibbs free energy term inside our exponential, right? And typically, all of this stuff, our enthalpy and our entropy here, can be assumed to be independent of temperature, right? And so these are kind of lookup values, right? And so that means what we can do is combine all this into a temperature-dependent mobility term, right? And we now have a grain boundary mobility that is the relationship between our Gibbs free energy change and our velocity, right? This is just like our D naught term, essentially. Right? And so what we end up with is these equations work with both 2D and 3D. Your geometric factor out front's a little different, right? But anyway, the main idea is we've got a mobility here where all the temperature dependent stuff is. Our change in Gibbs free energy is only given by the curvature, and our atomic or molar volume is given solely by the chemistry, right? So we have a grain boundary equation that looks that is very closely related with temperature, just like diffusion. I said that wrong. It's very closely related to diffusion because it's the same thing. It's atomic jumps across over a energy hump. Same mathematical form. Okay. So if we make an assumption that all of our grains are equiaxed, right? Meaning that our grain shape, there is no preferential elongation to our grain shape. Our grains in cross section tend to look like polyhedra, right? They're not much longer in one direction than the other. So we can assume then that this average curvature has to do with the grain size, that the smaller the grain, the higher the curvature, the larger the grain, the less the curvature, right? And that's what we saw in our soap film experiment, right? These fine grains tend to look like circles. These large grain boundaries, they look like straight lines. Okay, so if we just assume that the curvature is related to the grain diameter, we can then calculate what the average velocity is a function of the average grain diameter should be, right? So if we know our average grain boundary energy is this, and our average grain size is this, we get a mobility term and a fudge factor alpha out front, right? This is just a constant that's going to be kind of, sort of, maybe, hopefully close to 1. Right, and that allows us to relate the grain size to the velocity. So what this tells you here is they're inversely proportional to each other, right? The velocity falls by 1 over the grain size. So as the grain size gets bigger, our velocity is going to fall, right? Every time our grain size is doubled, our velocity is going to be cut by a factor of 2. It's going to go in half. All right. Okay. We also have other things that can slow down our grain boundary. So imagine we have a solute in our system that wants to segregate to grain boundaries, right? We've talked about that off and on a lot, right? That grain boundaries are great for accommodating solute, right? Especially solute that is larger than the surrounding matrix, right? The atomic size is larger. There's more free volume at the grain boundary. Therefore, the solute itself will cause less of a strain field if it's at the grain boundary. So having the solute at the grain boundary gives us an energetically variable, very favorable configuration, right? So if our grain boundary moves, we've now just put our system, we've increased the energy of our system, right? Because the elastic distortion caused by these solutes might be higher than the change in grain boundary energy that we've eliminated by making a grain smaller, right? By the amount of grain boundary interface that we've eliminated in a step might be very small compared to the additional elastic stretching on the bonds in some neighborhood. Okay, so what that means is that in order for the grain to move, the grain boundary to move, we also need to move the solutes along with it, right? And this is called solute drag. So what this says is that in many cases, the rate limiting step for grain growth is going to be the diffusion rate of these solute atoms in our system. Okay, and we can see this. This is a lead alloy with tin added, and this is the weight percent tin, and you can see that the grain boundary mobility drops exponentially with increasing tin content, right? Just 0.006% of tin in lead is enough to make it fall 4 orders of magnitude in grain boundary mobility. Okay, so this is broken down into random grain boundaries, and these are special, highly mobile grain boundaries. They're not as affected, but other grains, these are a very small fraction of the overall grain population, right? So in general, solutes can really slow down our grain growth. We also have the phenomena called Zener pinning, where small particles can slow down our grain growth, right? If there's 2 cases to consider. One, where the surface energy of the particle is much less than the grain boundary. The particle metal or particle ceramic interfacial energy is less than the grain boundary, and one where it's more, right? So let's just consider where it's less. The grain boundary, when it hits the particle, essentially we eliminate a small portion of grain boundary and replace it with some surface air energy here, right? I got to be really careful in how I say this. I don't want to rush just because it's the end of the class. So what we're going to do, so I don't inadvertently confuse everyone with trying to explain something too quickly, we're just going to stop here. Okay. We'll pick this back up on Wednesday. There's just a couple slides left for grain growth. And then for Wednesday, I haven't quite decided the order I'm going to go in. I think we're going to wrap up phase transformations with, or the crystalline phase transformations with martensite. And then the last topic of the semester is going to be vitrification and diffusion in glasses and polymers, amorphous systems. The final will be exactly like the midterm, same format, same rules, except much easier. Right. Okay. So keep an eye up. There's reading going up tonight. There's another homework going up tonight that's going to be pretty easy. Right. The homework is going to be largely qualitative. I know everyone's getting into the end of the semester, super stress time. So I said at the beginning, this course is going to be heavily front loaded, and a lot of people didn't believe me, right? So you'll have a fairly, very straightforward homework assignment coming up. But other than that, I think, and that may be the last official homework, just because we're coming up to the end of the term. Okay, everybody. Take care. Have a good one. Stay safe. Stay healthy. Is my video working now? Cool. Cool. Okay.